So now we can do double integrals using polar coordinates. Well, it's actually the iterated integrals, right? The double integral is just, right, a double integral of some function f over some region R of the xy plane, right? And depending on the nature of that region, you may want to switch to polar coordinates, right, instead of rectangular coordinates. So, quick review. Of course, you should know the conversion from polar coordinates to rectangular. They were on your formula sheets, and they will continue to be. And you should also know the reverse, right? To go from rectangular to polar coordinates, we'll just use these. And again, I'll use tangent theta rather than arctangent theta. So tangent theta is y over x, and just make sure that you know what quadrant you're in, right? So if you take the inverse tangent, that will naturally be somewhere between negative pi over 2 and pi over 2, whereas if you're in quadrant 3 or 4, for example, if x is negative and y is positive, you're in quadrant 2, then you'll have to add pi to get the correct theta. In any event, right? So those are the conversion formulas for polar and rectangular coordinates, right? And before we get to the double integrals, we might want to spend some time just doing, figuring out various regions expressed in rectangular coordinates and just convert them to polar coordinates, right? So here's an easy one. Suppose we have a set of points, x, y, in the plane such that x squared plus y squared is less than or equal to 36. Right. So our goal here is to rewrite this in terms of r and theta now, right? And I do say this is an easy one because, of course, this is just 1, 2, 3, 4, 5, 6. Right? This is just a disk of radius 6, a closed disk of radius 6, right? So in other words, r squared, of course, is just x squared plus y squared. So this is telling us that r squared is less than or equal to 36, which means r is less than or equal to 6. And that's it, right? So r is less than or equal to 6. You might say, well, wait a minute, shouldn't, right, because the radius here is positive, right? It's a positive square root. Shouldn't I also stipulate that r has to be, greater than or equal to 0? It's assumed, right? So you don't have to say this explicitly because we're assuming that r is naturally greater than or equal to 0. After all, that's how it's defined, right? It's defined this way rather than this way. So we really don't want to allow r to be negative. In some cases, of course, you're welcome to do that, and there might be cases where that might be necessary, but those don't come up very often here, right? So, yep, so that's it, right? So disk centered at the origin, pretty easy, right? What about a disk that's not centered at the origin? So suppose we have this set of points xy in the xy plane such that, let's say, x squared, let's do x squared plus y minus 3 squared is less than or equal to 9. Okay, so you should be able to figure out what this is. This is a circle whose center is 0, 3, right? So here's the center, 0, 3, and then the radius is 3. So I'm going to go up 1, 2, 3 more, and now we still have a disk. This time its radius is 3, right? But its center is 0, 3 instead of 0, 0. Okay. Yeah, and again, it's everything inside the disk as well. So all these points in here, right? I went a little bit outside. Yeah, so it's the set of points inside the disk as well as the boundary of the disk too. So these are closed disks that we're talking about. Closed because they include the boundary. They include the equal sign here. Right, so again, our goal is to change this to r and theta. Right, and there's a couple ways to do this, of course. You can just kind of, figure it out in terms of r as a function of theta. This is something you should have done in Calc 2. But in case you haven't, well, I'm going to go through it, right? So let's multiply this out, right? We get x squared plus y squared minus 6y plus 9 is less than or equal to 9. And in fact, let's just get the circle itself, right? Let's change it to equals, right? So this is going to be the circle, x squared plus y minus 3 squared equals 9. Because everything, right, the disk then is everything inside of that. So notice that 9 minus 9 is 0, and we just get x squared plus y squared minus 6y equals 0. Well, we know what x squared plus y squared is. We've seen that before, right? This is just equal to r squared. Right. And now what about y? Again, that's something you should know. Y is r sine theta. So change y to r times sine of theta, and that equals, sorry, that should be a theta, and that equals 0, right? Well, we could factor out an r here. In fact, we could just divide both sides by r because, well, r is only 0 at the origin, right? So we usually don't have to worry about just that single point. Right? So yeah, divide by r. Right? And then we just get r minus 6 sine theta equals 0. In fact, this is the equation of the circle. We can just add the 6 sine theta to both sides to express this r as a function of theta. Right? So that's the circle, right? That's the boundary here. R equals 6 sine theta. But what about the inside of the disk now? Well, right, so notice that r is the distance from the origin. So that's this distance. So everything less than that is going to be in the disk, right? So to get the disk, all we really need to do here is write r is less than or equal to 6 sine of theta. Right? So that's the answer, right? R has to be less than or equal to 6 times sine of theta. Sorry, my thetas look weird, right? But we have to be a little careful now, right? Because we didn't specify theta before, because we just naturally assume if we want the entire disk, theta goes all the way around, right, from 0 to 2 pi. So I suppose we should have specified that here. Yeah, so r is less than or equal to 6, and theta is between 0 and 2 pi. If you include 2 pi, then you're going, right, you're including 1 point more than once. So yeah, we should have specified theta. After all, if you only want the top half of the disk, if you only want this part of the disk, then theta would go from 0 to pi. And maybe we should include pi here, right? So, right, so yeah, we should specify theta as well. And in this case, we have to, because if we go from 0 to 2 pi, then you're including 2 disks, right? Because this, going from 0 to pi will include the entire disk. if you go 0 to 2 pi, then your r will be negative, and you're basically just doing a double disk here. You're going around twice. Make sense? So yes, so theta is only between 0 and pi here. We'll include both the 0 and the pi. Right? Yeah, I mean, just think about this, right? If you're at pi over 2, right, then r is going to be 6 times sine of pi over 2, which is 6. So that's the distance from the origin to the North Pole here, right? This is where r is 6. So if you go past pi over 2, say, 3 pi over 4, you're here. 5 pi over 6, you're here. So when you get to pi, you went all the way around the circle. You did not go around the circle twice, right? You went around the circle once. Or what I should say is, right, if you look in this circle here, if you only go 0 to pi, you're only going halfway around. But that's because, right, the center is the origin. You're including, right, the origin includes, is inside of the circle. It's inside of the disk. Whereas here, the origin is on the boundary of the disk, right? It's on the circle itself. So, yeah, so here's where you really do have to be careful, because if you go 0 to 2 pi, you're going around twice. You don't want two disks. You just want one. Okay, so, yeah, I mean, there are other examples, of course, but we'll see those later. I think the disk is a good one. You also get cardioids and other regions that are more conducive to polar coordinates rather than rectangular coordinates. So now we can get back to double integrals, and we already know how to convert a double integral to an iterated integral using Fubini's theorem, right? For vertically simple regions, we just do this, right? And then dA is dy times dx, right? Or for horizontally simple regions, you can do this. Right? So this is just a quick review of what we did in the previous video, in the previous section. But now dA is dx dy, right? Right. So, yeah, after all, if you just have a tiny rectangle here of length dx, and let's say the width is dy, the area, of course, is just dx times dy. Okay, but now we want to use r and theta, right? So in other words, we want to replace x with r cosine theta, y with r sine theta. And now the natural question is, what is dA in terms of r and theta? Okay, and you might think, well, that's easy. It's just it just has to be dr times d theta. But that's wrong. Okay, that can't be it. And it's just a matter of units, dimensional analysis here, right? Think about what dx and dy are here, right? These are lengths. So let's say dx is in meters and dy is in meters. So meters times meters is meters squared, or square meters. Well, square meters is an area, right? But here, dr, right, that's a change in radius, so that's a length. That's meters. But theta is not a length. It's an angle. Right? Angles are in radians, but radians are unitless, right? So this is meters. This is a length, right? This is not an area. Not an area. Right? So this cannot be our dA here, right? So what would make it an area? Well, we need to multiply by another length. The only length we have is the radius, r. So if we multiply by r, that becomes our dA. Okay, so there has to be an extra factor of r simply to make this into an area. Okay? Yeah, a lot of students forget the R, right? So don't forget the R here, because it is easy to forget. After all, when we do rectangular coordinates, we don't write y dy dx, right? That would be a volume, right? We don't write x squared dy dx. That would be quartic meters. So so yeah, don't forget the R, right? Because if you do, it's just not going to work out. You're going to get the wrong answer every time, or almost every time, I'd say. Okay. Yeah. Now, you may not buy this. After all, why is it just r dr d theta, right? Why isn't it 3 times r, right? Or pi times r, or 6.4 times r, right? So obviously we know it's not r squared, because that would not be an area anymore. That would now be a volume, right? Or the square root of r, for example, would not work either. So I'm not going to get too deep into this. This is something we can actually talk about later this chapter. Again, very briefly toward the end of the chapter. But just to give you the basic idea, right? So here's a sector of a circle. We have some fixed angle, and let's say it's a small angle d theta, right? And we have the radius r here, right? So what's the area of the sector? Hopefully you remember it's 1/2 r squared times theta. And in fact, theta here will just be a small theta. It'll be a d theta. And now what we'd like to do is figure out, well, if I change r, how do I change a? Right? So if I increase r by just a little bit, right, by just dr here, how does that change a? Well, take the derivative, right? Or in this case, the differential. What is the differential of a, right? It's the partial of a with respect to r times dr. And we already changed theta, so we're not going to do this. Although you can, if you want to change theta as well, increase theta a little bit. Oops, sorry. Right, so yeah, we already took the d theta. We're just interested in the change of r. Right, and so the partial derivative of 1/2 r squared with respect to r, well, it's just 2 times 1/2 times r. It's just r dr times d theta. Right, so that's why it's not, 3 times r or 2 times r or anything like that. This is a little bit hand-wavy here. I admit that this is not completely rigorous, but that does give you the basic idea that this little change in area here, this dA, can be calculated as r, or can be approximated as r dr d theta. Right? It's the differential approximation, right? It's not the delta A, but it's close enough. Yeah, and there's other ways to explain this, but this should give you the idea of why you need to multiply by r when converting from, dy dx to dr d theta. This is r dr d theta, not just dr d theta. Okay, so I hope that helps. Right. So here's the theorem that essentially, shows what we did more rigorously. Again, we're not going to prove it, but the idea is that this is the Fubini's version, right? This is Fubini's theorem, right, for polar coordinates. Because in the last video, we talked about Fubini's theorem for only rectangular coordinates, either vertically simple regions or horizontally simple regions. And this book really focuses on what are called R-simple regions. Right? In other words, they're regions where R might vary in terms of theta, but theta, just goes between 2 angles. So let's say this is angle alpha, and this is angle beta, right? But now r might be some function of theta. So it doesn't have to be as part of a circle. It could be any sort of a curve like this. So this would be g1 of alpha. This would be g2 of alpha. Right? And so that explains this notation here, that if you want to convert a double integral into an iterated integral using polar coordinates, you're going to go between two angles, say alpha and beta, right? Or you could use theta 1 and theta 2. You know, same idea here. The book likes to use alpha and beta, fine. And then your two functions of theta, so g1 of theta and g2 of theta for the inside integral. And then this will practically be just a function of r and theta. And then remember the dA is not dr d theta, it includes this r here, right? So, yep, so then we write r dr d theta, right? And of course, this function may contain another factor of r, so you may end up doing r squared or r cubed, but this r dr d theta, that's just the dA, that's just the change in area, right? Right. So yeah, that's your change in area, which is this yellow region in here, right? So that's the dA that we're talking about here. Okay. Actually, that's the area that you get after you integrate. Sorry. So it's a little bigger than just the dA, right? The dA is just a small slice of that, right? So just a small slice of this, and then maybe a small slice of that. So this little piece of it here is your dA. All right, so let's just do some examples. Okay, so first example, find the volume of the solid region between the paraboloid z is equal to 16 minus x squared minus y squared and the xy plane, right? So it's this region that I graphed here on the right, or it's the region right between the xy plane and the surface itself. So we're looking for the volume of what's inside here, right? That volume in there. Oh, I have just enough space to write this out. So, okay. So let's write out the definite integral. So, right, so the volume will just be the double integral of the function here. The function in this case, right, is just 16 minus x squared minus y squared, right, times dA. And of course, we can calculate this in rectangular coordinates using Fubini's theorem. So what's the region R here, right? What's the region R? Well, it's just this disk. See, it's this entire disk down here. And it might be helpful to graph it in 2 dimensions, right? So what is the radius of this disk? Well, right, this is the xy plane where z is 0. So x squared plus y squared is 16, which is 4 squared, right? So the radius is 4. So 1, 2, 3, 4, 1, 2, 3, 4. Right. So yeah, this red disk down here is just everything inside the circle of radius 4. Okay, so that's our region R. Okay, so yeah, so if you want this in terms of rectangular coordinates, well, we're going from the bottom half of the circle, which is y is equal to, negative square root of 4 minus x squared, to the top half of the circle, which is y equals positive square root of 4 minus x squared. And then x just goes from negative 4 to 4. So from negative 4 to 4 of the integral from negative square root of, why did I say 4 minus x squared, right? It is 16, isn't it? Yep, because the radius is 4, but r squared is 16. There we go. That was an easy fix. Yep, so this should be 16 minus x squared, or sorry, negative square root of 16 minus x squared. That's not 46. And then positive square root of 16 minus x squared. Right. So those are our functions of y, right? That's our g1 of x, g2 of x, and so on. And of course, we know what the function we're integrating. It's just 16 minus x squared minus y squared. And we did vertically simple region, right? So this is dy times dx. Okay, so you can evaluate this. I don't think it's going to be all that difficult. Actually, I take that back. I think it might not be, it's not as trivial as I thought. Because when you integrate with respect to y, of course, you're going to get y cubed. So you're still going to have that square root of 16 minus x squared. So that might involve like a trigonometric substitution. So, sorry, that's supposed to be a y. So probably not the best way to do it, right? This is doable, but not easy. Not easy. You really have to remember your Calc 2, your techniques from Calc 2. So it could be integration by parts, it could be a trig substitution, I don't know. But when you notice that the region here is just a disk, that tells me we should probably convert this using polar coordinates. So 16 minus x squared minus y squared, right, is just 16 minus the quantity x squared plus y squared, which is 16 minus r squared. So now the quantity we want to integrate is 16 minus r squared, right? And what is r doing? R is just going from 0 to 4, because that's the radius, right? dr. And then theta, well, we want the entire disk, so we have to go all the way around from 0 to 2 pi d theta. So it turns out this will be a lot easier to integrate. Of course, I hope you recognize my mistake. dy dx is not dr d theta. What am I missing? Of course, I'm missing r, right? This is r dr d theta here. So we need another factor of r. Got it? Okay, so now I'm completely out of space, so give me 1 second and I will rewrite this integral and start fresh. Okay, so yeah, so where were we? So we were trying to evaluate, or we're trying to find the volume of inside this paraboloid, right, in this region here. And we're going to do it by evaluating this iterated integral from 0 to 2 pi, from 0 to 4, of 16 minus r squared times r dr d theta, right? Right? And the usual way to do an iterated integral is just to do one and then the other, right? So first, let's integrate with respect to r. That's on the inside here. So that inside integral, well, this is just going to be, what, 16r minus r cubed, right? So yeah, we're going to have to integrate 16r minus r cubed. The integral of 16r is 8r squared. The integral of r cubed is 1/4 r to the 4th, right? Evaluated between 0 and 4. Okay. So this is going to be 8 times 4 squared minus 1/4 times 4 to the 4th minus 0, right? When you plug in r equals 0, you just get 0 minus 0. So that shouldn't be hard. Okay, so this is going to be 16 times 8, which is, I believe, 128. And then this will be 4 to the 3, which is 64. So 128 minus 64 is just 64. So our final integral here, the integral from 0 to 2 pi of 64, well, 64 is just a constant, and the integral of 1, right, now we're just integrating 1 d theta, so that's just theta evaluated between 0 and 2 pi. So we get 64 times 2 pi, or 128 times pi. Everyone okay with that? So that should be the volume, right, of this region. Right, so that's the volume of, again, the solid region, everything inside here. This whole paraboloid, or maybe upside down paraboloid, but it doesn't matter, right? If we just flip it right side up, right, and we say we stop, right, so if this is z equals 0, this would be z equals 16 up here, but then the radius would still be 4, and so the volume of that region would be the same 128 pi, right? We never gave units, so cubic meters or cubic feet or whatever it is, right? So, yeah, could we have gotten the same answer by evaluating this iterated integral? Sure. But this would be slightly harder. At least I think it will be. Yeah, because you're going to get, square root of 16 minus x squared times 16 minus x squared. And that's not an easy one. It's not basic substitution. It's probably trig substitution. So, yes, it could have been done using rectangular coordinates, but I think switching to polar coordinates made this calculation much easier. I went step by step by step here. Obviously, we could have skipped a lot of steps. And once you get used to this, this is a very easy calculation. But in rectangular coordinates, not so easy, at least not in this case. Okay, so that's our first example. And again, it just involves changing something from rectangular coordinates to polar coordinates. So here's another example. We want to sketch the region and evaluate the iterated integral. Okay, so essentially here we're going backwards, right? Here we're given the iterated integral. Now we want to, again, we want to evaluate it, but before we do that, maybe we can make some sense by what this integral represents, and just look at the graph here, right? So, yeah, so where are we going? We're going from r equals 0, which is, of course, the origin, to r is equal to cosine of theta. So what is r equals cosine theta? So hopefully you know what it is. If not, let's go through and maybe convert this to rectangular coordinates where it's a little more familiar. Remember, cosine of theta is what? X over r, right? So x over the square root of x squared plus y squared. So when you cross multiply, you get square root of x minus, the square root of x squared plus y squared squared, right? You're just taking the square root, multiplying by itself, and that just equals x. So x squared plus y squared equals x. Well, if that doesn't look familiar, why don't we subtract the x from both sides? And now that equals 0, so we get x squared minus x plus y squared equals 0. So if I complete the square here, I can think of this, right, as x minus 1/2 squared, because this is just 2 times 1/2, right? But then I add a 1/4 here, right? So I also have to subtract a 1/4 to keep it the same. And then I can add the 1/4 to both sides. Oh, I forgot the y squared, of course, plus y squared, right? And that equals 1 over 4. So this is just the circle, right, of radius. Remember, this is r squared, so the radius is not 1/4, it's just 1/2. And the center is the point 1/2, 0. So let's graph that, right? Let's make this 1/2 here. This is 1, so 1, negative 1. Right? And if the origin, if the center is this point right here, and I probably shouldn't use yellow for the center, I'll use green. So if that's the center, the circle, of course, is just this. Okay, so yep, this is r equals cosine of theta. Right. Right. So it's a circle, but right, it's not a circle centered at the origin. Right, it's a circle whose center is 1/2 0. Right, x equals 1/2, y equals 0. And the radius is not 1, right? The radius is only 1/2. Okay. But I hope you would agree that if you look at the two equations here, this one on the left, r equals cosine theta, is a little bit simpler. No, I mean, that's just my opinion, but it looks simpler to me. Right? So that's what we're getting, right? And we're going from negative pi over 2 to positive pi over 2. Right? In other words, we're just rotating from the negative y-axis to the positive y-axis, and that should fill in the entire circle. Right? In other words, what we're getting is the area of this circle. Right? So that's what this double integral represents. This is the area of the, oh, I shouldn't say the area of the circle, right? The area of the disk, right? Or the area inside the circle. You can say that. But the area of the circle itself would be 0. So the area inside the circle, right? And this circle here, right? Or this one here. Okay, so now let's just evaluate the double integral. And we get what, hopefully you know what the answer is by now, but let's just evaluate it just to make sure. So we're going from negative pi over 2 to pi over 2. And then r goes from 0 to cosine theta of r dr d theta. So it's an r. All right, well, do the usual thing, right? Do the inside integral first. So the integral of r is 1/2 r squared, right? Evaluated between 0 and cosine theta. Okay, the 1/2 we can pull outside. That's just a constant. Pi over 2. And this is just going to be cosine theta squared, or cosine squared theta, right? Minus 0 squared, which is 0. So now we just have to evaluate the integral of cosine squared. And you should know that. That's a Calc 2 problem. If you do, first of all, I think it's on your formula sheet. This comes up often enough where at this point it should almost be second nature. But I think I'll go through this one last time if you don't remember how to evaluate this, right? The trick is to use the identity that cosine squared of theta is 1/2 times 1 plus cosine of 2 theta. Okay, so this is an identity you should remember from your trigonometry days, or you can look it up. Right, it comes from the half angle formulas, I think, or double angle formulas, or half angle identities. I forgot what they're called, but I do remember the formula. So we get another 1/2, that's 1/4. And then we're just integrating 1 plus cosine of 2 theta d theta, again, from minus pi over 2 to pi over 2. Squeeze that in there. Okay. Well, this is just the sum of two integrals, right? So we get the 1/4, the integral of 1 d theta, from, again, minus pi over 2 to pi over 2. And then the hard one, we have 1/4 the integral of cosine of 2 theta. And that will require a substitution, but a very easy one, right? U is just going to be 2 theta, So du is 2 d theta. So we need to multiply by 2 and divide by 2. And that will transform this into 1/8 the integral of cosine of u du. Now, u is 2 times theta, so 2 times negative pi over 2 is just negative pi, and then we go to positive pi, right? But let's do the first integral. The first integral is just, right, 1/4 times theta, evaluated between negative pi over 2 and pi over 2, so that's just pi over 2 plus pi over 2 is pi, right? Yeah, well, I hope you can do that in your head, right? Pi over 2 minus negative pi over 2, right? Pi over 2 plus pi over 2 is pi. So you get pi over 4, right? Now, for the second integral, when you integrate cosine, you just get sine of u, evaluated between minus pi and pi. But remember, sine of pi is 0, and sine of negative pi is also 0. So you really just get 0 minus 0 here. So you get pi over 4 plus 0 minus 0. So we just get pi over 4. So that's the area of the disk, right? Pi over 4. So no surprise. After all, remember the radius is 1/2. So pi r squared is pi times 1/2 squared, which is indeed pi over 4. So hopefully you knew that already, that we were going to get pi over 4 for the area. But it's also, right, so this iterated integral then represents the area inside the disk. Okay? Yeah. All right, well, yeah, I guess that's it. We'll do another example. Okay, so we want to find the area of the region R, and it's given to us in polar coordinates, right? R and theta. So R is less than or equal to 1 plus cosine theta. So it should be less than or equal to 1 plus cosine theta. And theta just varies between 0 and 2 pi. Okay, so, yeah, so to do that, we're just going to evaluate, right, the double integral of 1 dA over the region R, right? So if you remember, this represents the area of region R. So now we just convert that to an iterated integral, and you can see that they're basically giving this to us. This is not going to be hard to convert. Theta just goes from 0 to 2 pi, right? And then R goes from 0, I mean, how do I know that? Remember, R is always going to be bigger than 0, to 1 plus cosine theta. Right? So that's the outer boundary of the region R. Right? And right, we're just finding the area. We're not finding the volume. So this is just 1 times dA. Right? So this is 1 times dA. But remember, dA is not dr d theta. No, it's r dr d theta. You need to multiply by another r. Okay. All right, so again, I don't think this is going to be that bad here. The way to evaluate this integral is do the inside integral first, save the 0 to 2 pi for later, and we're just integrating 1 times r, which is 1/2 r squared, evaluated between 0 and 1 plus cosine theta. Okay, so leave the 1/2, and then what are we integrating here from 0 to 2 pi? We're integrating 1 plus cosine of theta, the quantity squared, right? Minus 0 squared, but, well, that's just 0, right? Okay, so far? All right. We should probably multiply this out. I mean, right, because I don't think we're going to be able to substitute u as 1 plus cosine theta. So if we multiply it out, we get 1 plus 2 cosine theta plus cosine squared theta. Okay, so we're essentially splitting this into 3 separate integrals here, right? One of them is completely trivial, right? We're just integrating 1. The second one, the 1/2 times 2, will be 1. And this is just the integral of cosine theta, and that's almost as easy. But then we do have this part here. It's the 1/2 times the integral from 0 to 2 pi of cosine squared theta. Now that should look familiar, right? We just did this, right? We just did this. We had 2 different limits here. Remember, that was from negative pi over 2 to pi over 2. So with these limits, we don't conclude automatically that we're going to get 0 here. Although, yeah, I don't think we can conclude that here. I don't think it is. Okay, so the first integral should be pretty easy. This is just 2 pi, 1/2 of 2 pi minus 0, right? And when we integrate cosine, we get sine, and that's evaluated between 0 and 2 pi. And so that's going to give you 0 minus 0 as well, right? Sine of 2 pi is 0, sine of 0 is 0. So, right, so here we get 1/2 of 2 pi is just pi, and then we get sine of 2 pi minus the sine of 0. But that's just 0 minus 0, right? So, right, so those parts are not difficult. Yeah, this part's going to, we could go through the same trick again that we did in the last one. Or we could just use the formula that's on your formula sheet. Let me see if I can pull that up. Yeah, so it gives you both versions, right? It does give you the formula for cosine squared. Let me use a different color here. So it does tell us that cosine squared is 1/2 times 1 plus cosine of 2 theta, and we can use that the same way we did earlier. But it also gives the formula for cosine squared of x dx, and that's just going to be 1/2 times x plus 1/2 times sine x times cosine x, right? Plus c for indefinite integrals. Right, but this is a definite integral, so let's see. Notice that we have a 1/2 here, so times 1/2 is going to be 1/4. And here x is theta, so this is theta evaluated between 0 and 2 pi, and then plus sine theta cosine theta. Remember, I pulled out the 1/2 already, evaluated between 0 and 2 pi. Okay, so this is 2 pi minus 0 plus, well, again, sine of 2 pi and sine of 0 is 0, right? And cosine of 2 pi and cosine of 0 is 1. So it's really 0 times 1 minus 0 times 1, which is just 0. Right? But notice we still have 1/4 of 2 pi, which is just pi over 2. So we get pi plus pi over 2, so we're going to get 3 pi over 2, right? So, yeah. So not a completely trivial double integral, but the answer is 3 pi over 2, and that's the area. Okay. Oh, the area of what? What is this region R? Right. So maybe we should go through that and see what it is we're finding the area of. Because I think in other problems they might actually specify to graph the region, and maybe we should do that here. So let's graph this region R in the xy plane. All right, so when theta is 0, remember cosine of 0 is 1, we get R is equal to 1 plus 1, which is 2, right? And here's 1, here's negative 1. And cosine of pi over 2 is 0, so, right, so when when theta is 0, we get 2. When theta is pi over 2, we get 1. When theta is pi, remember cosine of pi is -1. 1 plus -1 is 0. So we're back to 0. So what we end up with is this region here. You connect the dots, and you get something like this, right? And then, so that's just between 0 and pi. When you go to 2 pi, you effectively get the same region. Oh, I went a little too far there, maybe. Yeah, it should be symmetric, right? Yeah, and if you look sideways, if you tilt your head to the left, you'll see this. So it kind of looks like a heart, right? In fact, that's the description of this. That's the name of this region here. This is called a cardioid. Right. Cardioid, right? So it's just, you know, heart-shaped. Right. So yeah, the area inside this heart, this cardioid, is exactly 3 pi over 2. Okay. So that's the area we just found, the area of that red region in there, that cardioid. Okay, and again, this, right, you have the formula for the integral of cosine squared and sine squared. I think I even put sine cubed and cosine cubed because they also come up once in a while as well. And so maybe we'll do one last example of that. Okay, we want to evaluate the double integral of x, right, dA, over the region R. R is the region inside the circle, x minus 1 squared plus y squared equals 1, for y is greater than or equal to 0. Right, so I think first thing we should do, of course, is graph the region. So, right, so by now you know this is just a circle of radius 1, but it's centered at the point 1, 0. And notice y has to be greater than or equal to 0. So it's only the top half of this circle here, right? And in particular, it's what's inside. So, yep, we're just going to get the area of that disk in there. Oh, no, sorry. We're not going to get the area, right? Because we're not integrating 1. We're integrating x. So, no, this is the region R over which we're integrating. Okay? This will not represent the area, right? What we're integrating is x. Right? If you like, what does this integral represent? This actually represents the following. Let me try to do it this way here. So this is the x-axis, this is the y-axis, this is the z-axis. And the region R in the xy plane, let's see, so it's going to be, yeah, this region here maybe. And if I can graph it a little bit darker there, that might be helpful. Oh, now I messed up the R. All right, so this is the region R. This is the region R. Right. So what we're getting is going to be a volume, right? If we graph the function z, right, as a function of x and y, it's just x, right? So what is z equals x? It's a plane, right? It's a plane that's going to be kind of tricky to graph here, right? It's going to be this plane here, right? So if this is the z-axis, this is the x-axis. It's the plane that goes up like this, 45 degrees, right? Z equals x, coming right out of the plane, right? Yeah, z equals x, right? So yeah, it's going to be essentially the volume underneath the plane, but above the region R. So what happens is you get this volume in here. I know that's kind of a mess, but maybe I kind of probably drew it wrong here. Right. So this region R is effectively over here, and you're getting the volume underneath a plane, but above the region R. Okay, so this is going to be a volume, essentially, right? Okay. Anyways, our task is to evaluate this double integral. Right? So, of course, we could use rectangular coordinates, right? I mean, it's given to us that way in terms of x and y, right? That's the circle here, this circle. X minus 1 squared plus y squared equals 1. On the other hand, we should also probably convert this to polar coordinates. Yeah, I think it will be easier. I think it'll be easier to evaluate this in polar coordinates. Or let's put it this way. Even if it's not, let's stipulate that we have to use polar coordinates. So using polar coordinates. Now we don't have a choice. All right. All right, so first thing we need to do here is remember that x is r times cosine of theta, and dA is r times dr d theta. Right, you get that extra factor of r in there. All right, so now our double integral will be an iterated integral, and what we're integrating is r squared times cosine theta with respect to r and then with respect to theta, right? Yeah, the r squared comes from r times r, of course, right? All right, now how do we determine this equation in polar coordinates? Well, we've done it before, right? You just rewrite x as r cosine theta, y as r sine theta, right? Figure it all out. In the end, what you're going to get is that r is going to be 2 times cosine of theta. Okay, so yeah, work it out. This is what you should get. So that's the same circle here. All right, it's the same circle, but expressed in polar coordinates, which, again, I would claim that this is easier than this, but that's just my opinion. So, yep, r varies between 0 and 2 cosine theta. What about theta, right? So if you're thinking 0 to pi, after all, this is just half of a circle. If a full circle is 0 to 2 pi, and half the circle is 0 to pi, well, think again, right? So here's theta equals 0, right? Here's theta equals, I don't know, 30 degrees, pi over 6, pi over 4, right? This might be pi over 3. This might be, 5 pi over 12. I don't know, right? But when you get to the y-axis, we've covered the entire disk. And the y-axis is 90 degrees, pi over 2. So, yep. I warned you about this a little bit earlier, right? That when your disk does not contain the origin, when it's only on the boundary of the disk, right? You get this situation where this half of the disk is only covered from 0 to pi over 2, not 0 to pi, right? Yeah, we talked about this earlier. In fact, we went all the way around for the whole circle, and we only went from 0 to pi, right? Or actually, in this case, I think negative pi over 2 to pi over 2. But yeah. So yeah, we're only going from 0 to pi over 2. If you make the mistake of going 0 to pi, you're going to end up getting like double of what it should be. So be careful of that. All right, so yeah, we have to evaluate this iterated integral. And again, it's not trivial. This will take some time. Now, we're integrating first with respect to r, right? In other words, we're doing this inside integral first here. But the cosine of theta doesn't depend on r, so we could bring that outside. That will come up for the second integral, the theta integral. So for the first integral, we don't need that there. We're just integrating r squared with respect to r. Sorry, with respect to r, right? So yeah, this is the first integral we need to evaluate. Okay, so when you integrate r squared, you get 1/3 r cubed. The 1/3 is a constant. That comes all the way outside. And that's supposed to be a pi over 2. Pi over 2, right? Keep the cosine. That'll come up later, right? And now we just have r cubed, evaluated between 0 and 2 cosine theta. So when you plug in 0, you get 0 again. Again, don't count on that. That won't always happen, but I think it does here, right? So, and then 2 cubed is 8, and then cosine cubed. So we're going to get 1/3 times the integral from 0 to pi over 2 of cosine theta times, well, I'll write it out again step by step, right? It's just 2 cosine theta cubed, which is going to be 8 times cosine cubed. So the 8 can come outside. And now we have cosine theta times cosine cubed theta. That's cosine to the 4th. Okay, so yeah, so now we have to integrate cosine to the 4th. And if you look on your formula sheet, you only have cosine cubed. We don't have cosine to the 4th, right? So yeah, we can't just resort to the formula sheet here. So what can we do with cosine to the 4th? Well, it's really just cosine squared, right? Squared. And we know what cosine squared is, right? That's just 1/2 times 1 plus cosine of 2 theta. But then we have to square it, right? So we're going to get 1/4 times 1 plus cosine of 2 theta squared. And then when we square all that out, we're going to get 1 plus 2 times cosine of 2 theta plus cosine squared of 2 theta. And, well, let's keep going, right? This is going to be 1/4 times 1 plus 2 cosine of 2 theta. And now cosine squared, right, is still 1/2 times 1 plus cosine of 2 theta. But be careful, it's 2 times 2 theta now, right? So you're actually going to get 4 theta. So yeah, you expand all this out and you kind of get a mess here. You get 1/2 and then another 1/2 times cosine of 4 theta. So let's see, if we pull out, well, 1 plus 1/2 is 3 over 2, right? Plus 2 times cosine 2 theta plus 1/2 times cosine of 4 theta, theta. And now let's just distribute the 1/4, right? So we're going to get 3 over 8 plus 2 over 4 is 1/2 cosine of 2 theta, and then plus 1/8 cosine of 4 theta. Okay, so in this form, I think we should be able to evaluate this integral. We'll just split it up as 3 separate integrals. So the 8 over 3 will multiply everything, right? So the first integral from 0 to pi over 2 is just 3 over 8. Of course, you know, that cancels the 8 over 3, so that'll be easy. And then we get the integral of 1/2, so I'll pull out the 1/2. Again, 0 to pi over 2 of cosine of 2 theta. Okay, so that's not hard. That's a simple substitution, right? And then we get another 1/8 integral from 0 to pi over 2 of cosine of 4 theta. Okay, so I'm going to do this a little bit more quickly here, right? You get 8 over 3 times 3 over 8 is just 1. So this first integral is just the integral from 0 to pi over 2 of 1 d theta, which of course is just pi over 2. No surprise there. the second integral here, so we get 8 over 3 times 1/2, that's going to be 4 over 3. And then because of the substitution, right, you're going to use u as 2 theta, you get another 1/2. And then when you integrate, you get sine of 2 theta evaluated between 0 and pi over 2. Oops, pi over 2, right? Right, and then for this integral here, we're going to get what? So we have the 8 over 3 times 1 over 8 is 1 over 3. And then here, our u is going to be 4 times theta, so now we're going to have to pull out a 1 over 4. And when you integrate, you just get sine of 4 theta evaluated between 0 and pi over 2. So I hope I didn't go too fast here because I did the integrals already, and now we just have to evaluate, right? Okay, so this will just be 2/3 times the sine of, well, pi minus the sine of 0. So that's just 0. Oops, sorry. Plus 1/12. And then this is going to be sine of 2 pi minus the sine of 0. So that's also just 0. So in the end, we just get pi over 2 plus 0 plus 0. So the answer, after all that, pi over 2. Okay, and remember what that is, right? That's not an area, right? We're not integrating, we weren't integrating 1, right? We're integrating x. So we can think about this as the volume of this region in here, this blue region, or this purple region if you consider the region here to be, you know, half of a disk. So this is a volume, right? This is the volume specifically under the plane z is equal to x, and above the half disk, well, it's just the region R, right? The region R is this half disk up here. Right, here it is one more time. So here's 1, here's 2. So it's right, yeah, it's just this half disk here of radius 1, but centered at the point 1, 0. Yeah, so again, not an easy one, but one where we had to actually evaluate cosine to the 4th. So that's not too uncommon. In this section, you will be evaluating, you know, integrals of, say, sine cubed, or, you know, cosine to the 5th. That could happen. I still maintain it's probably easier than sticking with rectangular coordinates, although I'm not sure here. Maybe not. Maybe it isn't. So this could have been more difficult than the rectangular coordinate version. On the other hand, it's nice to get used to the polar coordinates because it does come up a lot more often than you would think, right? So I hope this helps. So a lot more examples and a lot more exercises in the homework. Best of luck.